Hey everyone, so this should say class 82 at the top, not class 64. And we looked at this new idea called critical angle, total internal reflection, and by the end of the class, you should be able to describe the conditions necessary for this to occur. It's important to note that this is not a Regents topic, but this is a topic I do expect you to know, and it's closely related to what we've been doing with Snell's law. So the do now is just a bit of a review. It says light is traveling through lucite. So right there we know that N1 is of lucite, which is 1.5. And it strikes the boundary between lucite and water, so that's N2 of 1.33. At an angle of 34 degrees, draw the incident ray. So theta 1 is 34 degrees. Now, as far as this next bit, there's two ways you could do it. First thing, you have to be able to draw a 34-degree angle. And there's two ways to do it. You can either do option A, where the light ray goes like this, and this is 34 degrees. Or you could, and this is the way I usually do it, that's 34 degrees. Okay, either one of those is correct, as long as the 34 degrees is with respect to the normal line. All right, so let's do a little Snell's law. N1 sine theta 1 equals N2 sine theta 2. So N1 is 1.5 sine of 34 degrees. And N2 is 1.33 sine of theta 2. Remember, I'm not really going to spend too much time showing all the steps in the algebra. So I'll throw this in my calculator. Let's see, we have 1.5 sine of 34 divided by 1.33. And then you still have to take the inverse square or the arc square, or excuse me, the inverse sine or the arc sine of whatever that was. And you should get something like 39 degrees. So theta 2 equals 39 degrees. All right, and what does that angle look like? Well, it's always going to go into the opposite quadrant, so it looks something like this. I'm going to exaggerate it a bit, but this would be 39 degrees. Just make sure that, in preparation for the tests, Regents exams, you are able to draw an angle at a specific angle. So if I say draw 34-degree angle of incident, be able to do it with a protractor. If you then solve for the angle of refraction and it's 39 degrees, be able to draw it with a protractor. So then we started looking at some videos, some examples of this thing called total internal reflection. Basically, total internal reflection occurs when you go from a high index of refraction to a lower one. And if you hit the interface between the two surfaces at a large enough angle, what'll happen is you're not going to go into the new medium. You're actually just going to reflect right back into the original medium. The PhET simulation I have right here for number 2 does a really good job of showing that. If you say, for example, you set the top material to water and the bottom material to air and play with the angle of incidence, what you'll realize is that at a certain large angle and all the angles past that, the light only reflects inward. It does not refract at all. So for number 1 here, it says when light travels from a medium of higher index of refraction to a medium of lower index of refraction, the light ray refracts, let's go back to black, refracts away from the normal. What happens when light bends away from the normal, quote unquote, too much? It reflects entirely back to N1. This is referred to as total internal reflection. I refer to this frequently as TIR. The angle at which this happens is referred to as the critical angle. That's different for every combination of N1 and N2. So if N1 is water and N2 is air, there's a certain critical angle. If N1 is glass and N2 is glass and N1 is air, it's a different critical angle. Okay? We're not going to get into the math behind how to find critical angle. It's not really too hard. But for this class, it's just not really something I want to focus on. So I've kind of been alluding to it, but total internal reflection only occurs when N1 is bigger than N2, because that's when we refract away from the normal. Again, if you refract away from the normal so much that the refracted ray of light lies along the interface, what happens is you get only reflection. Why can't total internal reflection occur? When traveling from a low index of refraction to a higher one. So for low to high, low n, to be specific, to high n, light refracts toward normal. So this picture on the right, I think, does a really good job of showing what total internal reflection looks like. Again, those videos on the previous page do a good job too. But let's see, number 8 says, the light traveling through a transparent optical fiber, so this is like how we get internet, always hits the internal boundary of the optical fiber at an angle greater than the critical angle, so that all of the light is reflected and none of it is transmitted. So the angle I'm referring to is this angle here, just to zoom in. That angle right there is the angle of incident, and that's greater than the critical angle. So for example, if the light came in at, like, let's say this angle, like came in there, that's greater than the critical angle. That would be an even bigger angle. So that would result in total internal reflection as well. If the light came in at too steep of an angle, for example, I'm going to look over here at this one. If the light came in kind of like this, that might be too steep of an angle. And see, that's a pretty small angle right there. Therefore, it might not occur in that case. So the critical angle for light and glass fiber is 65 degrees. Name 3 angles at which total internal reflection will occur. So I just made up that number, but that's a reasonable number for total internal reflection to occur at for the critical angle. So again, it has to be greater than or equal to 65 degrees. So let's make angle 1 65 degrees. Angle 2, 67 degrees maybe. And angle 3, some people are saying like 100 degrees, but actually it can't be. It can't be greater than 90, so it's got to be greater than the critical angle, or equal to the critical angle, but less than 90. Let's go with like 87 degrees. So in summary, for total internal reflection to occur, you could read it here, but basically you need 2 things. So you have to satisfy both these criteria. Criteria 1 is N1 must be greater than N2. Criteria 2 is that the angle of incident, that's theta 1, must be greater than the critical angle, which I would have to give you. So let's look at a few of these. In each situation, explain why total internal reflection will or will not occur. Let's go through one by one. So for this first one, I could tell you right away, it will not occur. The reason being, N1 is less than N2. So right there, we know it cannot occur here. I'm not even looking at the angle. Let's look at B. So if we look at B, let's see. It looks like, yep, N2 is greater than N1. That's good. Or excuse me, N1 is greater than N2. And it looks like this angle here, I think we measured to be like 55 degrees. Is that greater than the critical angle of 50? Yeah, it is. So theta 1 greater than theta C. So this one checks out. So look at this one here. Again, we can eliminate this one. Just looking at the n values, N1 is less than N2. Remember, N1 must be greater than N2. Must be going from high to low for this to work. So let's see, does the n value check out? Yeah, N1 is greater than N2. So that's good. Now let's look at the angle. Now this angle here, I think was only like 33 degrees. I'll say 30 degrees. So it cannot occur here. Theta 1 is less than the critical angle. Therefore, it cannot occur here. So there's only one case it can occur at, because you need to satisfy both criteria. N1 is greater than N2, and the angle of incident is greater than the critical angle, which was given to us here, 50 degrees.